So hi everyone, I'm Chadi Akel from the University of Versailles, and I'm going to present to you a tool developed in our team called CERE, which stands for Codelet Extractor and REplayer, based on LLVM. So the motivation for this tool is that we know that finding best application parameters is a costly, iterative, and time-consuming process. Because every time you try a new parameter, like changing the number of threads or trying new compilation flags, you have to re-execute the whole application to evaluate the impacts of these changes. So we believe that CERE can reduce that benchmarking time by breaking applications into standalone codelets. So standalone codelets are small pieces of code that you can extract from the original application and replay independently from the application. It means without running the rest of your application. So this can make costly analysis affordable because you can only focus on a single hotspot if you want to see the impact of a hotspot, of the new parameters on a hotspot, and also by regrouping similar codelets together. I will explain later what similar means here. You can select one representative per cluster, and based on the performance of this representative, extrapolate the performance of the other codelets in the same cluster. So this is basically how the extraction and replay process works. So you can choose to extract a loop from a source file like C, Fortran, C++, and other languages. And first, before executing the code that you want to extract, CERE will first dump the memory needed to replay this loop after. Then at replay, CERE extracts this loop into a wrapper which is in charge of restoring the memory and execute the code of the loop. This is the full CERE workflow, and the input is an application or a set of applications. And as you can see, there are two main steps, capture step and replay step. At capture, CERE will first detect hotspots in your application and extract for each of them the memory needed to replay it after. There is an optional step here with what we call invocation and codelet subsetting. It's a step where you can reduce the number of codelets you need to replay to predict the performance of the full application. So this step is costly. The capture step is costly, but you pay the price only once. Then you can replay a codelet as many times as you want. So at replay, you can choose to replay any codelets you already captured. And this is where you can retarget your codelet. It means you can compile it and execute the region you extracted on a different architecture, or also try new optimization like flag compilation flags. The output of this step is a binary which contains the wrapper that I showed in the previous slide, which is in charge of restoring the memory and warming up the cache. And here, before running your binary, you can change runtime parameters like number of threads or affinity to evaluate the impact of these new parameters. So since codelets are really fast to execute, you can quickly have, based on the performance of your codelets, a prediction of the performance of the full application with these new parameters. CERE extract codelets from hot loops or from OpenMP non-nested parallel regions. So I'll first talk about the faithfulness of the replay, then show you some applications of the tool, and finally present a small demo of the tool. So in order to use these codelets as a proxy for your application, we need to be sure that the replay is faithful to the original region inside the application. It means that what you will see at replay is truly what will happen in the application with your new parameters. Then we must also be sure that the codelet are retargetable. It means we can modify runtime and compilation parameters. So we can extract codelet traditionally either from assembly level or at source level. Both have pros and cons, but if we extract at assembly level, we are sure that the replay, the codelet version and the original version share the same assembly code, so we believe that the replay should be faithful to the original performance. But it's hard to retarget since you can't recompile assembly code, or you have to support various instruction set assembly to rewrite your assembly for new architecture on your processor. If you extract at source level, and this is what we have done before, the codelet will be easy to retarget since you can even change the source file, you can change the compiler, so it's freedom for the user to try everything. But we proved in a previous paper that the assembly generated is not necessarily the same. Why? Because when we extract at source level, we really take the code into a new source file, and then the region is out of its context. And it doesn't trigger the same optimization at compilation. This is why the assembly, it's hard to obtain the same assembly when we extract at source level. Also, from a developer point of view, we have to write a parser for each languages, and also a parser that is able to detect each kind of loop or region in this language. So finally, what is new here, and what we believe is the best trade-off between both extraction level, is to extract at LLVM intermediate representation. Since the code stays in its context, the assembly code generated is usually the same, and also it's retargetable since you can recompile IR code on a new architecture, on another architecture. And also, we benefit from the LLVM front end, so CERE is able to extract region from any languages that LLVM is able to compile. But sharing the same assembly is not enough to guarantee that the replay is faithful to the original region. We must be sure that the codelet executes the same code and works on the same data. This is why we have to capture register and memory states, but also OS state like file descriptors or socket. But unfortunately, CERE is not able to capture such region because we work at user land space and not kernel space. So the good point is that CERE, the tool, doesn't require any kernel module, but we cannot capture and replay, for example, loops that make IOs like reading or writing into files. Finally, we would like the replay also to be accurate for the performance, because if the region you extract was, for example, in cache in the original application, you also want that this region, this loop, must be in cache also at replay. So this is why we capture a cache state. And NUMA ownership is also important for OpenMP for a parallel application that runs on NUMA nodes, because we know that when the memory is touched for the first time by a thread, this memory is allocated on the NUMA nodes where that thread belongs. So this is something we need also to record and restore at replay. So this slide shows how the memory capture works. So traditionally, to capture memory, we trace every memory accesses and we really save what is touched by this instruction. This is really precise, but also very slow. So we work at page granularity. We work at page granularity, so it's coarser, but also much faster. How does it work? Before capturing the region you want to extract, we protect, just before, we protect all the memory allocated by the program. Then once in the region, if new memory is allocated, we intercept this allocation. We actually allocate the memory, but we protect new pages allocated. So when memory access happens, it generates a segmentation fault since the memory is protected. And with our segmentation fault handler, we can deduce the address of the page that has been touched and save this page to disk. Finally, we unlock the page and return to the program, which continues its execution. So the dump footprint is small because we only dump touched page. Also, to record the cache, to save the cache, we start this process earlier and we record the last pages that has been touched. And at replay, we reload them in the same order. We replay them in the same order, and we believe that data will be in cache like in the original application. To capture NUMA first touch, we added a small mechanism that records for each page the first thread that touched it. So I'm going to show you some applications of the tool, but just before, we know that there are redundancies in applications. There are two kinds of redundancies. The same code can be called multiple times, so the same loop can be called multiple times with different data, and also codelets from different applications can have the same performance signature. So here in this plot, we see that for a loop from the spec Tanto, this loop is called more than 3,000 times. So we are not going to capture 3,000 different data sets and replay all of them. It will be really, really slow. So we trace the full invocation of the loop. For each invocation, we have the performance in cycles. We clusterize by the performance, and we see that we have 4 classes of performance. So it's just necessary to select one representative per class, and by replaying these 4 representatives, we can predict the performance of the full loop. So we use this approach for fast performance prediction across architectures. So we provide hotspots from the NAS benchmark on an LLVM architecture, and we attach for each codelet, we attach a performance vector that contains metrics such like vectorization ratio, cache misses, that are enough to characterize the performance, the signature performance of this loop. Then we clusterize together codelets that are similar. It means that have close vector performance. And we select only one representative, which is the closest to the centroid of the cluster. And since all these codelets are in the same cluster, we believe that they will behave the same. So we run the representative we selected on different architectures. And with the performance of this representative codelets, we can predict performance of other codelets in the same cluster and reconstruct the full performance of the application on these architectures. The results, you can see the results here. So the reference architecture is an LLVM, and we tried on Atom, Core2, and Sandy Bridge. And this is the speed up compared to the LLVM performance. So in red, it's the real speed up. So we really took the NAS benchmark and we ran them on each architecture to see the performance. And in yellow, it's the predicted speed up based on the Codelet replay. So as you can see, the prediction is quite accurate. And what is important is that it was 31 times faster to use Codelet than running the full benchmark on these architectures. Since Codelets are really fast to execute, we can pay the price for compilation flag exploration. If you want to try to find the best combination of compilation flag for a full application, it's impossible. The space to explore is too huge. But with Codelets, since they are fast, we can pay this price. And here we tried for a Codelet from the NAS SP benchmark to explore 1,000 combination of flags. And we found more than 400 schedules that are better than the default O3 flag. Executing this region is 150 times faster than running the full SP benchmark, but also this approach allows to create what we call a hybrid binary. It means a binary where each hotspot have been compiled with its best flag. Finally, we also used Codelet for scalability projection. So we extracted a region for an OpenMP, for the OpenMP SP benchmark, and we execute it, we run it by varying the number of threads. Still in red is the real time, and in yellow the prediction with the Codelet. So the running on different architecture, we can see that every time running the Codelet is faster, more than 20 times faster than running the full SP benchmark, and also the scalability prediction is also accurate and close to 90%. Okay, I can show you a small demo of the tool. Okay, so I'm gonna just a simple example to show you how we can extract and replay a loop from a BT for the BT benchmark. So the first step is to tell CERE how to build and run your application. So this is with this command. Okay, and then the next step is we want to know what loops we can extract from this application. So you can ask the tool to output the regions that we can extract. Okay, and the output is a CSV file. Where is that file? Okay, here. That contains, it's here, sorry. That contains all the loop you can extract from the BT benchmark and with different information like the source file, the line, and the function where this loop is. So I'm just going to extract this loop, which outputs the results of the BT benchmarks in the standard output. So if it works, it means that it will print exactly the same output than the original version. So first, we can capture, we have to ask CERE to capture this region. Okay. So when you capture, as I said, we cannot capture region that makes IOs. So there is a hidden step where CERE detects if this region is doing IOs, but we accept output to the std out because you can replay a print to the default output. So it's dumping the memory of this region. So it takes, as I said, it's a slow process. It takes some time, but I think it's. I know why. Sorry. Okay. And then I will replay this region. Okay. So the demo effect or. Okay, what's going on? Of course. Okay. So this is the thing that works 100 times and then doesn't work at live demo. Okay, sorry, I don't know what's going on, but I'm gonna try again, maybe, I don't know. Okay, I think it doesn't work. Okay, I don't know what's going on. I'm gonna try the flag exploration I wanted to show after this demo that doesn't work. So I swap to the FT benchmark, and if it works, we will be able to replay, we will be able to replay a codelet by varying the number of threads. Sorry, not the number of threads, the compilation flags. So same step, we say how to compile and run the application. Okay. Then we can detect hotspots here in FT. We can ask CERE to detect hotspots automatically for you. So with this command, okay. So it uses the Google Perf tool to instrument the application and to detect hotspots and generate the call graph for this application. So this is working. Okay. So the FT. So the output, as I said, is the call graph. Okay, it's so big, really big. So you can see, you can find here the full call graph of the application, and for each loop, it tells you the execution time, the percentage execution time for this region. So here we can see that this loop is the hotspot for the application. Is a hotspot that takes more than 70% execution time. So we can try to capture it. I hope it's going to work. So first we have to do the full trace, of this region to detect representative invocations. Okay. So this command actually traces, this is the plot I showed previously, it will trace the full execution of the loop to detect actually the representative invocations that we need to capture to predict the performance of this region. So this is, again, okay. So the output of this command is the clustering of this is the full trace of the loop, and here we can see the clustering of the performance, and it tells you that to predict this more than 35,000 invocation, we only need to capture one representative invocation and replay it. This is done automatically. So we just ask now to capture invocation required. Okay. CERE. Yes. Okay, here it works. So I don't know why for BT it doesn't work. And so here we capture this region. We can replay it. So we can replay it, and nothing happened because it just replayed the region. But we can see, based on this invocation performance, we predict the overall performance of the loop. So you can try a new flag to see what is the impact. If you change compilation flag, you can quickly evaluate the impact on this region. So here, if you go in the next file, we can change to 03. And hopefully, when we run the replay again, performance should be, I have to force it. Okay. So in 00, we had this performance, and with 03, it's twice faster. So this shows us that we can use Codelets to try new compilation flags, other compilation flags, and try and evaluate the impact of these new compilation flags on the replay, and then evaluate the performance of the full loop and the full application. Okay, I go back to the presentation for the conclusion. So to conclude, CERE breaks application into faithful and retargetable codelets. It is used for piecewise auto-tuning, so we can select architecture, compiler optimization, or predict scalability of full applications, and also other exploration that are costly, like energy prediction and so on. We don't support region performing IOs, like reading, writing into a file, and we cannot modify the source code since the replay will break. So this is also a limitation, and we are tied to LLVM since we work at higher representation. Finally, you can find the full accuracy report at this address. And this concludes my presentation, and the CERE tool is available on GitHub under the LGPL license. Thank you.
Okay, we have 2 microphones set up here. If anybody has questions.
So if I understood correctly, you said this works, you capture and you can replay on multiple architectures, but I guess the right limitation is you can only replay on systems that follow the exact same binary interface.
Sorry, I didn't hear the end of the question.
So am I correct in understanding that the replay has to happen on a system that has the same ABI as the system on which you captured?
The same ABI?
Yeah.
Yes, because we.
Right.
Yes.
So
yes,
it's
correct.
You can replay on different microarchitectures, but not different instruction sets, for example, different architectures that way.
Sorry, I don't hear you.
Oh, sorry. So you can replay on different microarchitectures,
yes,
but not on different architectures.
Yes, for now we only tried on different microarchitectures, and there is a prototype for that we extracted on Intel architecture and replayed on an ARM, but it's still a prototype and with a lot of hacks. So yes, you're right. It's replaying on for now on the same microarchitecture. Yes.
Okay. So, but you're working towards trying to solve the problems there.
Not for now because we are kind of tied with Intel architecture. But yeah, it's doable. It's something that we can do. But yeah, there is no real technical limitation for this.
I also had a second question.
Okay.
I see the results are all on floating point heavy programs, I think. Are the results as good also on programs that are maybe a bit more pointer
yes,
chasing or different kinds of styles of programs?
Actually it's a report because there is an output for the tool that there is a powerful command actually. You tell CERE, okay, extract everything from this application and give me the Codelets that have the smallest replay time and cover the maximum of the application runtime. And these results are on this is the results I'm talking about. Actually, I have the result in here, but with this with the format, it's broken. So, but this is for NIMD from the spec, and for each loop, it gives you the clustering, the replay time, and the coverage of this region. And finally, it's a summary of what you can perform on this application with the tool. So here we can extract more than 98% of the execution time with this, I don't know, 10 Codelets. This was the question or no?
No, it was a slightly different question, but we can
sorry.
take it offline.
Okay.
It's fine. Thanks.
Okay, thank you.
How do you compare with other code extractor?
Sorry?
How do you compare with other code extractor like the Codelet, like SimPoint or others?
Yes, the difference with SimPoint. Okay, I'm going back to the. We compared our tool with SimPoint and other extractor like Aztec, Code Isolator. So SimPoint is extracting that there is a lot of differences because SimPoint is extracting at assembly level, and you have to replay it on a simulator. So you have to. It works with a simulator. This is not the case with our tool, and also okay, this is the big difference with SimPoint actually. So the benefits of our tool is that the Codelets are retargetable. We can use them to test performance of new architectures on your benchmarks. Thank you. Okay, thank you all.